Now let's focus on the effect of this kappa term. The kappa term is a term that is proportional to the second derivative of x. What does that term do? Can somebody give me a kappa to use? So I'll basically make u equal to 0 and kappa equal to what? 1? Okay. So can you please come and draw initial condition for u equal to 0, which is no advection, but kappa equal to 1?
Oh dear.
Sorry. I think let me try again. I think the computer must have thought you lifted this above the screen. Okay. All right. So now that's the solution. Completely different, right? So what's the behavior of this solution? It looks like a damping term, right? But does it damp it all the way to 0? No, it's still not 0, right? So what's the damping like? Huh? It seems to damp to its average, right? So yes, the like a constant function is a steady state. So maybe a better way to describe it is a smoothing term, right? So if you start with the oscillatory initial condition, it seems to become smooth very fast, right? And actually the magnitude of kappa tells you how fast it becomes smooth. So in this one we see, maybe we see it became smooth too fast, right? So let's try a smaller one. What do you want me to do? How small would you like to see it? 0.1, okay. And I think the last person to come, can you come over please and draw a initial condition for u equal to 0, kappa equal to 0.1 to see how fast or slow the solution gets smoothed out. All right, cool. So here we see the solution gets smoothed out to something like a sinusoidal wave in a much slower way, right? And once it becomes a sinusoidal wave, it's already pretty smooth. The rate of decay becomes pretty slow. All right. Okay, what do you think if kappa is negative? It flips? No? It'll blow up? Yeah? Okay, let me try. So I don't want any of you to come and draw something that blows up, so let me try myself. Alright, so I'm gonna draw something pretty smooth to see what it'll look like. Alright, it blows up instantaneously. I don't see anything here. Okay, so kappa equal to negative value actually never appears in something physical. All right, so well, let me take it back. Unless, so whenever you see a negative, you see a negative term here on the right hand side of an equation, partial differential equation, a negative second order derivative, two things can possibly happen. One thing is that the equation actually can run backward in time instead of forward in time. The equation actually has a solution. Don't laugh. There is a famous equation in finance called the Black-Scholes equation that models the price of some derivatives that actually runs backwards in time, and it has I think it has something like this with a negative kappa. And another possibility is that there is a stronger term, for example, the fourth order derivative, that dominates this term, which prevents it from blowing up. But usually, most of the time, we see a positive second order derivative. All right. Now, the last thing we want to do is, now what if we have both u and kappa? That's usually the case. Can somebody give me a combination of U and kappa? 0.25, sorry, 0.25 and 0.75. And can you come draw initial condition?
Oh, I think I touched
Start from
outside.
start from the beginning. Yeah, I can place here.
Wait, do I have to press like?
Yeah, you have to press continuously.
Oh, I
once
think,
you
like,
once you
how-
lift, once you lift, it thinks you're done.
Yeah. There it is.
All right. It's pretty similar to what we had just with kappas, right? Can you stay and get me
Yeah, I can get something.
something
more
that is
interesting.
cooler? Let's close. Can we do?
Faster to you.
Wait. What happened?
Doesn't want to end that.
Okay.
There it goes.
Oh, sorry. Shouldn't do that one. Can you give me a different combination?
So, what were interesting ones? You could go. Wait, what ended up with negative? What did it, like? What was U negative?
Just goes the other way.
That was uninteresting. We could go with like U over 1. I doubt that's gonna be productive.
What's wrong with that?
Yeah, we could do that.
Do what?
Like 1.
All right.
We'll see how that goes.
Okay. Draw something.
Something sharp.
Yeah.
That's
Oh,
why go to
there it
the-
goes.
Cool. So we can see that almost instantaneously the sharp edge gets diffused, right? Gets smoothed out, and then the whole thing still goes towards the right. All right. So that's the effect of advection and diffusion. And if you remember what we saw on the airplane, it's kind of similar, except for there is a source term, there is a generation of the vorticity at the leading edge always. So as you can see, the vortices goes downstream, it gets advected and also diffused, right? So that's actually very similar to the equation you have drawn. And at some point, there is the linear equation we are here no longer is valid, and the vortex actually breaks up, because here the W is actually not small compared to the free stream. All right. Now, any questions on this second order derivative term we call diffusion term? Or some people also call dissipation. All right, and advection, some people also call it convection. Yeah, so this equation is what people call advection diffusion equation, convection diffusion equation, advection dissipation equation, whatever people use to describe these two terms. All right, so that's the first type of equation we'll focus on this semester.